Yeah, hello everyone. As you've said, I'm Marius. I'm from the FU Berlin, but that's fine. Like there are too many universities in Berlin. And I'm at Jens Eisert's group. I'm in a third-year PhD right now, and I will be talking about this recent paper that we had about the learnability of output distributions of local quantum circuits. Let's just start with who contributed to this project. There was like a lot of people, and everyone did, a lot of work for this to come to the end product. So thanks to everyone who was involved. And yeah, let's just dive in. The presentation I will just start with giving like a motivation of why we even want to consider this problem of learning the output distributions of quantum circuits. Then I will kind of specify the problem a little bit more concretely. I will talk a little bit about how one accesses data, whether one accesses samples or something called statistical queries, and how that relates to like the kind of learner that you have in mind. In particular, we have in mind like generic learners. I will explain what I mean by that later on. And if we have time, I will give a very rough sketch of the proof, which allows us to lower bound the query complexity for our problem. And yeah, there's at the very end, I will just mention that we have a second kind of result in the paper, which is like the positive result, if you want to call it this way, that in fact, if you have Clifford distributions, there's some structure that you can exploit, and then you can actually learn these efficiently. So let's start with the motivation. In machine learning, there's one task that people consider, and it's so-called generative learning, in which the task is the learner is given data which might be coming from a very complicated distribution. This data, you might think about it, for example, I don't know, pictures of cats or something like that. And this learner is then asked to somehow output samples himself, which follow a distribution which, in some meaningful way approximates the real distribution from which the original data was coming from. And now, one particular incarnation of this kind of generative learning setting that people have been studying in the context of quantum machine learning in the last couple of years is something called quantum circuit born machines. And basically, if you just compare the two pictures I've drawn, I've just kind of unpacked the black box, which was the learner. And now the learner kind of consists of two black boxes. One being the model and one being like the algorithm. Here the model is now some parameterized quantum circuit, and the algorithm I just consider, it's like a classical algorithm which it kind of just tries to compare the real distribution from which the data is coming from to a hypothesis distribution at some time step. And at the end, the goal would be that after a certain number of steps, you converge to some distribution which, again, in some meaningful way approximates the real distribution. And the way that this usually is done is that you kind of you output samples from your parameterized quantum circuit, and you compare the distributions. Then you do some kind of optimization, I don't know, some gradient descent, and then you update your parameters of the quantum circuit. And yeah, I mean, because I wasn't sure like what exactly the audience is, I just wanted to mention the distribution that the hypothesis distribution that we're talking about here is the Born distribution of when you start with some in the O0 state, you apply the circuit and measure the computational basis. Okay, so why are these interesting? These kind of learners are interesting because people believe that they could give rise to quantum advantage in machine learning tasks, and you know, there are some reasons why one could believe that this is true, namely, you know, these are highly expressive settings, and also there has been proven quantum advantage, in fact, for a very fine-tuned setting in which you encode like a discrete log problem into a stochastic process. But of course, you know, like for practical purposes, this is not sufficient. You would want to have quantum advantage for like more natural data, essentially. And it's often conjectured that this is still the case, and I guess there's even maybe some numerical evidence for this. But often the argument that is being done for why you could expect to get a quantum advantage is kind of following the lines of, you know, there are these arguments about hardness of sampling from random quantum circuits, boson sampling, etc. And therefore, somehow there's the belief that, you know, because that there isn't basically, there will not be any classical learner that could essentially learn the output distributions of quantum circuits, but these quantum circuit Born machines could, and therefore kind of you would get a quantum advantage there. And this kind of led us to the question of asking whether, you know, is that even true? Like, you know, basically we wanted to understand whether these quantum circuit Born machines are even capable of learning themselves, basically whether they can learn distributions generated from quantum circuits themselves. So to formalize this a little bit, the concept class that we will consider is the distributions generated by local quantum circuits of some fixed, some depth d. And when I mean local, in this case, I will refer to geometrically local, where I mean like you have this kind of brickwork architecture, and the distributions is what you get when you measure in the computational basis. Now the two local gates here, or basically the gates, they, of course, you have a gate set that you assign to it, but I will usually like drop that for using this of, you know, for it to be a bit more clear when I write. I will just drop the gate set, but it's always, you know, it should always be in the back of your mind. And the task here is that, you know, given some samples from measuring in the computational basis, you want to output some generator, like an algorithm, which itself is able to sample from a hypothesis distribution, which is in total variation distance close to the real distribution with a high probability. That is kind of the task that we have in mind. Yeah. But because I was saying that really what we're interested in is like, you know, applying this to like a real life kind of scenario. We were thinking about, okay, how do generic algorithms work? I mean, here again, just go back to the picture that I had drawn earlier, where you have the algorithm and the model, right? And now, like the algorithm, it has to somehow, you know, decide between the two distributions. If you don't have some kind of promise on the data structure, it's a bit difficult a priori to make kind of you know, kind of make this this algorithm compare on the basis of samples, individual samples, but it will typically do this using the statistics of the distribution. So essentially, it's kind of comparing expectation values of functions with respect to either the ideal or the hypothesis distribution. And there's a nice theoretical model which kind of captures this, which is called the statistical query model. I mean, it was, you know, this was kind of conceived for a completely different reason, but we actually see that it can be applied here very nicely. And basically, in this setting, what you consider is that the algorithm doesn't get access directly to the data, but actually it queries a function and gets back an expectation value of that function, which is some tau tolerance close to it. And in fact, if you now choose tau to be something that is, you know, inverse polynomial, then basically you can just see this like as a formalization of what I said about generic learners, that they will just you know, use like compare based on expectation values, because with an inverse polynomial tolerance, you can simulate this statistical query oracle. Yeah, and this is what a real life kind of learner would then do. And
excuse me, for clarification reason,
yes.
you are mentioning in this statistical query that you are approximating the expected value of some function. But what function is involved here?
Yeah, these are basically any kind of, you can query any kind of function which is you know, in some interval. That's the only limitation on F, or on phi, sorry.
So you're for every individual query, you can basically take a different function.
Exactly. Every query is a new function. That's exactly what I mean.
And then it gives you the expectation, or sort of an approximation of the expectation with respect to that function.
Exactly. It will give you back a number v, and that is just like
basically the expectation of that thing, or approximation.
Exactly.
Okay.
And then, as I said, if now your tolerance is not too small, you can always kind of simulate this oracle yourself.
Okay, thanks.
Okay, so basically now we have kind of you know, refined or adapted a little bit our initial question about you know, the learning the output distributions of quantum circuits. but now basically we don't have any more access to the samples themselves, but to the queries, to such a statistical query oracle. As a formalization of what I said about the generic learners. And we want to ask, how many queries do you actually need to learn the concept class of output distributions? And how does that actually depend on the gate set? That's another question, of course. Because, maybe it appears a bit more plausible that if you have universal gate sets, that that this could be hard, but maybe for like some restricted gate set, this could be a bit more easy to do. Which brings me to the first result, which is that for d larger than log n, there's a super polynomial lower bound on the query complexity for this problem. And okay, this holds for any universal gate set, but in fact, it also holds for the Clifford group, which is a bit more surprising, maybe. I mean, because as I said, it's not a universal gate set, so it might be a bit more surprising. And as a result of this kind of challenges a little bit the intuition regarding quantum advantage using these quantum circuit bond machines, because you could argue a little bit like if these quantum circuit bond machines cannot even learn themselves efficiently, why would you then assume that they would have some quantum advantage on other data sets? I mean, of course, it's not a proof. It's just it's kind of like a challenge to that intuition. And now, of course, if you want to prove something about a particular data set, then you would have to, look into that as well. So I think my next slide would be, I would go into the proof sketch. So before I do that, yes.
Sorry, what was on the proof side? What was D exactly? Is that the number of
the queries?
For D larger than log n, we find the super polynomial.
D. That's the depth of the quantum circuit.
That was the depth of the quantum circuit. Okay.
Yes.
And so, I mean, I'm still a little bit fuzzy on the goal. So I have such a circuit.
Yes.
Which may be Clifford circuit or whatever. And now I'm trying to learn its output distribution. And the only thing that I'm allowed to do is to ask these queries, these expectation queries.
Exactly.
And the algorithm that's trying to learn is what? Is a BQP machine, or?
So
it's one of these machines itself.
So exactly. So like this is the interesting, another interesting observation. Basically, what we prove here is not. It doesn't even. It doesn't care what the algorithm itself is. It's just a lower bound on the number of queries. It basically kind of tells you that even if you had a quantum algorithm or a classical algorithm, you would still need at least super polynomially many queries to that oracle.
I see.
So, and that's why it kind of challenges a little bit this quantum advantage idea, because okay, maybe you have a quantum advantage, but if it's in the super poly regime, then I can barely talk about an advantage there, right? Because if it takes exponentially long, even for the quantum computer, okay, then what have I gained, essentially?
Why is that? I don't quite see but maybe we should move on.
No, I mean,
quite see the intuition with this quantum advantage, because what can you explain that again, maybe?
Yeah. So so the idea is, okay, if as I said, it's just a challenge. It doesn't rule it out, of course. Maybe you have some data sets for which you could show that you can, with few samples, learn it, and then you could maybe show a quantum advantage still. But for this task, for example, this particular task of learning the output distributions of quantum circuits, what we've shown is that independently of your algorithm, whether it is a quantum or a classical algorithm, it would always still require these super polynomially many queries. And therefore, it's a bit, like, okay, at least for this task, it's meaningless to talk about an advantage.
Okay, got it. Yep, thanks.
And somehow this task itself of learning, the class itself, it is like a meaningful task, at least we believe so. Yeah, so before I just jump into the proof of the sketch of the proof, yeah, if there are any other like conceptual questions about the setting and the results, like go ahead and ask them. Otherwise,
can I ask a question, please?
Yes.
Question is, how significant is it that you fix the initial state of the circuits to the all-zero state? So it's known that you can learn Clifford circuits very well if you can run them n times on initial states of your choice. Result by Richard Lowe. And you restrict the starting state here to just be the all-zero, which in particular means, I think, that you will never sort of see everything of the circuit. For instance, if the circuit has a few Z gates initially in its first layer, you will never see the effects of that. So it's like you're sort of tying your hands behind your back by fixing the initial state to be all-zero.
Well, actually, so I don't know if this will answer your question, but in fact, we also have we have this hardness result in the statistical query setting, but actually we also show that you can still learn the output distributions of Clifford circuits when you're given access to samples. This is like the second result that I will mention at the end. So this actually there isn't like a contradiction with the result that you mentioned, I believe.
Can you then say again, what is the negative result in the second bullet here?
So the negative result is like that you cannot, that you will need like super polynomially many queries in the. Am I frozen or?
You were just now, but now you speak again clearly.
Okay. Sorry, my internet is a bit unstable, unfortunately. But yeah, I was saying the negative result is about the fact that you will need super polynomially many queries in this statistical query model. And the positive result in that sense is the fact that when you actually have access to the samples, you can learn Clifford distributions efficiently.
I see. So we can interpret this also as sort of a weakness of statistical queries in comparison with having direct access to the samples.
Exactly.
Thanks.
Yeah, there's like a gap. At least for Cliffords, there's a gap.
And I guess the issue is because of the tau, because the sort of the tolerance is non-zero.
No, the reason that you get this, and I will talk about this a bit later, but the reason that you get the learnability when you get samples is that there's a lot of structure in the output distributions of Clifford circuits.
I see.
And this is then this kind of binds back to what I said at the beginning about the generic learners. Yeah, if you have a very structured data set, then you can come up with like fine-tuned learning algorithms. But of course, the learning algorithm which we have for Cliffords, if you gave it like some other data structure, it would not succeed at all. So it's not generic, and that's why these two are like kind of complementary, and there's like many different ways that you can kind of interpret them.
Okay, thanks.
If I can go on this point, from a high perspective, it seems that your message basically is information theoretical.
Exactly.
And that makes me wonder to what extent it is actually related to the quantum nature of your circuits. Suppose I build classical circuits involving randomness in the components. Would then the same technique give a similar result?
Absolutely, yeah. yeah, this is also possible. I think this I'm not sure now, right at the top of my head, if there is exactly a result like this for statistical queries, but I might be blanking out just right now. So, but it is definitely possible to apply this technique also for classical circuits.
Because that would suggest that indeed it's just a matter between discriminating the information you get from samples versus the information you get from these statistical approximations of expected values for functions.
Can you repeat the question? I wasn't...
That would suggest that indeed the result boils down to discriminating the power obtained from collecting samples from the power you get from collecting these statistical tests.
Yes.
Okay, then I'm again at the right page. Thanks.
Yeah, but in fact, actually, it's known, like this statistical query model is actually in general rather powerful. Like there isn't that many known examples of learning problems for which you get this kind of separation between the sampling, like where you get samples and where you get statistical queries. So actually the separation that we get here with Cliffords, to our knowledge, is the second separation after the learning parities, essentially. Like learning parities is also hard in the SQ, in the statistical query model, but it's easy when you have access to samples.
Thanks.
Okay, so then unless there are any other like conceptual questions, but anyway, like you can of course ask them again later on, but then I will just try to jump a little bit into this proof sketch. So as usual, like when you consider complexity theoretic problems, you often kind of want to reduce your problem to some other one. And here we're reducing the so-called many versus one decision problem to our learning problem. This many versus one decision problem, which I will just refer to the decision problem, just for brevity, is the following one. You're given the full description of some distribution rho R, which is the reference distribution, and ask you statistical query access to an unknown distribution, which is promised to be either the reference distribution or be coming from some set of distributions B, which doesn't contain R. And the question is whether you can decide whether A or B is true with high probability. And it kind of makes intuitive sense that if you have a learner for the set, like the set of quantum circuits, quantum circuit distributions, then they will also be able to solve the decision problem for R being some distribution in the set of output distributions. In particular, you could choose the uniform distribution as because, as we will see, this is a good kind of choice. And then kind of the task that remains is to lower bound the query complexity for the decision problem itself. Now, like I want to give an intuition of why. So basically what we do is we do this and we find like a super polynomial lower bound. But I would like to give maybe like an intuition of why you get this super polynomial lower bound. The reason for that can be viewed as follows: like it's known that the output distributions of local quantum circuits are typically rather flat, so they're not like not very spiky. No particular outcomes are much more probable than others. And in order to distinguish like these flat distributions from the uniform distribution, you would require very fine-tuned queries for to do so. And basically, because you have many of these, and you need for each of them, okay, let's take the worst case example situation where each of these distributions needs one query to be distinguished from the uniform. Then you would need essentially as many queries as you have flat distributions in your set. And because these are many, you get like a big query complexity. Does that make kind of sense? I think intuitively, to me at least, it makes. But if you have any questions about that, because I think afterwards I will like go a bit more into details here. Okay, so then this notion that I just described is captured by something called the randomized statistical dimension, which is something that Feldman has. He came up with that a couple of years ago, and this characterizes the query complexity for the decision problem. He's shown this. Now, like, what is this randomized statistical dimension? Okay, let me again. I'll just start from something a little bit different, but which is a bit easier to understand. So suppose like you have this set of distributions. What is the process this algorithm for deciding this decision problem? What would they do, right? Like they would query a function, and basically all the distributions which are like tau far from the expected, all the distributions which give you expected values which are tau far from the expected value with respect to the uniform distribution, it's, you know, they're covered by that function essentially, and are distinguished from the uniform distribution. So like essentially, if you wanted to know what is the query complexity for the problem, you kind of ask about what is the minimum cover of this set of distributions via these functions. And yeah, maybe pictorially is what I kind of tried to draw here. You know, like each function kind of covers a certain number of distributions, and you want to know like what is the minimum number of functions I need to query in order to cover the whole thing.
Something about that, Marius?
Yes.
The previous slide. Like this seems to characterize the non-adaptive query complexity. So if you sort of decide in advance which phi i's to query.
Yes. So that's why it's kind of like it's bounding it. It's not it's not like giving you the exact number.
But there's typically exponential gaps between the adaptive and the non-adaptive query complexity in problems.
Mm-hmm.
So,
yeah. Like I don't have now the exact. There's some. I mean, Feldman has kind of looked into, like, he has proven how exactly the bounds go here, and it gives you at least a lower bound on the query complexity.
Well, it should give you an upper bound on, and maybe also a lower bound on a non-adaptive query complexity. But
yes.
But not necessarily a lower bound on the adaptive complexity. And unless maybe in this particular model, adaptive and non-adaptive don't matter much, but I don't know.
Yeah, I must say, okay, I don't know the answer to why that doesn't matter there in this query model right now on the top of my head, but yeah, maybe we can look at this later on. But yeah,
I think it should also give a lower bound actually, because it somehow says, it should somehow say, or you can interpret it as with one single phi, what is the most number of sets or instances you can distinguish from each other, or you can so you basically you can cut the whole space with how much by one single query. And then that should give you a lower bound on the total queries that are needed.
It's not clear to me, but we can talk about it later.
Sort of like a binary search kind of thing. Like, well, but what is the best query to ask so that you can reduce the possible sets as much as possible, and then sort of the log of that or something should be a lower bound on the number of queries.
Mm-hmm. Yeah, yeah. Maybe we can go over this later on, but it's a good point, I think. So, yeah, it's actually though difficult to actually bound the size of this minimum cover in some meaningful way, and therefore this other quantity, this randomized statistical dimension, was introduced, which itself also is able to give you a lower bound on the randomized query complexity. And essentially it's equivalent to considering a randomized cover of this space of this set of distributions that I just considered here. Like you consider drawing functions according to some measure, and then you want to see how many do you need to cover the same space again. And yeah, this randomized statistical dimension is essentially the same to that notion. Right. Okay, now this is a bit ugly, but let's just try. So what I've on the top here is the definition of the randomized statistical dimension. And in particular, it's interesting to see that it is like a supremum over some measure mu. So actually, any mu will give you a lower bound, but of course, depending on what mu you choose, it might not be a very tight one. So kind of the task that you have to do when you want to get lower bounds for these problems is to find a good measure over your set of distributions. And kind of the quantity here in brackets, this probability, is kind of the probability that a randomly drawn distribution, according to that measure that you specified, will be distinguished from the uniform distribution by some function phi. Of course, you then take this max over phi to kind of get the maximum distinguishability, essentially. And I mean, to me at least, it's a bit difficult to pass this equation just on the first go. So it's not the goal here to do so. I just wanted to I just needed kind of to present it so that I can tell you what we kind of did. But basically, as I said, your task is to find a measure that will give you a good bound, and we came up with some measure which allows us to express this this probability here as this fraction here. And what is this fraction now? It's again the probability of distinguishing the distribution generated by a randomly drawn Clifford, now randomly drawn Clifford circuit from the uniform circuit over the probability that such a distribution is far from uniform. Yeah, again, it's a bit difficult to get an intuition of why that comes out, but you can again, yeah, see this probability of distinguishing somehow because like what I said before, it's kind of related to this fact that you have very many very flat distributions, and so this probability here will in general be very big, because when you draw a random Clifford distribution with high probability, it will be flat and therefore indistinguishable from the uniform distribution, but at the same time be far in total variation distance from it. Okay, I mean, maybe just take it for given that this is kind of what comes out, and or we can talk about it later if you have more, or maybe, no, you go ahead. Like if you have any questions, like ask them now, maybe about why that makes sense or so on. Otherwise, I'll just keep going. Okay, so now to upper bound the numerator, we actually just make use of some, just standard Chebyshev inequality, and then bounding the variance of this expectation value over the Clifford, like over the Haar measure with respect to the Clifford group. And then we use the fact that the Cliffords are two design, which then allows us to kind of calculate the moments, and this basically then gives us an exponentially small probability for this distinguishability. And for the denominator, there's like many ways that you can actually go about it to bound that, but the most straightforward way was just adapting an argument by Aronson and Chen, where they showed that actually the probability this probability of a randomly drawn uniform circuit distribution being far from the uniform to be constantly big. And we kind of just adapted to Cliffords essentially. So yeah, basically then, given this, these two, you get, let me see, is it clear? Like, okay, now you have like this inverse exponential here, and if you go back to the definition, it gives you an exponential query complexity, because you take the inverse of the, because here you have the inverse, right, for the randomized statistical dimension. Yeah, I think I was not very clear on this part, so ask questions if it was so confusing. I think it was maybe a bit confusing. So
can I ask, how does the depth of the circuit come in here? I never see a D dependence in the two bullets.
Right. Okay. This is actually on the next slide.
No.
So we now here considered, like for what I presented right now, we just considered linear depth like 9n or something like that, so that we can construct the whole Clifford group. And the rest of the proof in the paper is then all about reducing that depth, or like basically adapting that depth. And then there are different ways to do so, like before, like when you have the full Clifford group and you have the Haar measure over the Clifford group, it's very easy to compute these moments to bound the variance this variance. Here, like this variance here. But if now you don't have the full Clifford group, there's still some techniques that you can use, which are much more complicated, but you can actually still obtain bounds for these objects. it's these, they call like these statistical mappings that I guess Nick Hunter-Jones has used in the past, and also they've been used a couple of times in the last couple of years in the literature to basically, calculate moments when you don't have a true design, but you have local. The local gates are Clifford gates. So basically, this kind of first result kind of tells you that any gate set which includes Cliffords will for this it will also be a hard task, because you will also need like exponentially many queries. But you can actually also adapt the proof, because really the Cliffords only came in for the fact that they are two design. So you could adapt this to any universal gate set, because it's known that universal gate sets will converge to approximate T designs in depth and poly T. And by that, you can then exactly reproduce the same arguments again. So it holds for universal gate sets, but it also holds for Cliffords. The Clifford result, because the Clifford group is not universal, might be a bit more surprising to some. But also, this kind of then leads to what we said earlier, or what I mentioned earlier about the fact that we kind of have also the second result where we say, okay, what about if we had samples and not just these queries to the statistical query oracle? And here what we find is that as I mentioned, the Clifford output distributions can be efficiently learned with samples. And I'm not going to go into like much here, but the intuition why this works is the fact that that the output distributions of Clifford circuits are uniform distributions over affine subspaces, and this is a very highly structured data set, and all you kind of need to do now is to come up with an algorithm that from the samples learns a description of the corresponding affine subspace. And that is possible. And therefore you get this kind of separation between queries and samples, statistical queries and samples. And this is kind of leads to the open problems that we still have. For the general quantum circuits, one could ask whether this task remains still hard, even when given access to samples, because as we said, Cliffords are highly structured, but general quantum circuits, the output distributions of those, it's not clear that there's structure there that you could exploit with such a tailored algorithm. The other problem, which kind of relates a bit to also some, like this paper of Scott from a few months ago, which was retracted, about learning free fermion distributions. This is also kind of a fully open question. I mean, he thinks that it's possible. We tried to adapt our proof technique to match-gate circuits or free fermion distributions, and the bounds we get there, they are not, basically we don't get any meaningful bounds. So at least this technique doesn't rule out that they are learnable. But it's still completely open to answer this question. And of course, match-gate circuits, they are a bit more structured than the general quantum circuit. So this could be like a good try to like conceive algorithms which learn these. And the other thing that we think might be possible is for constant or like sub-logarithmic depth Clifford circuits to devise a learning algorithm which is still efficient in the statistical query model. For example, that's just you know, it's easier like just to start with some constant depth distributions, Clifford circuits, sorry, and even I don't know, two-layer Clifford circuits, but we don't know yet how to prove this, or if it's even, yeah, if it's true or not. So yeah, these are some open problems which if you're interested in, could have a look at. But this would be it from my side, and yeah, I think that's pretty good with the time. So I will stop here.